There's two different ways, at least, that we can get to the ideas of fluid statics. Fluid statics are the rules that govern when there's no velocity. The u component, v component, and w component are all equal to 0. So if we take the Navier-Stokes equations, which we know are very general and apply to all flows, and u, v, and w are all equal to 0, well, acceleration due to global change with time, that's 0. Acceleration due to fluid motion, well, u and v and w are all 0, that's 0. The viscous stresses, u is still 0, that's all 0. The only thing that's interesting is there's a pressure gradient and a force due to gravity, and they're going to balance each other out. So nothing moves, just about everything cancels out, and we're left with 0 on this side equal to -1 over rho di p di x plus g of x. Just these two terms out of the Navier-Stokes equation. If we rearrange, di p di x equal to rho g of x. If we integrate that to solve, we get p equal to rho g of x times x plus a constant. Or if if P is equal to P naught, some base pressure at some x location x naught, then that'll give us a solution for our constant. And P will equal P naught plus rho gx times x minus x naught from our integration. Or P minus P naught, the difference between the two pressures, is rho g x minus x naught. Or, if we convert to elevation coordinates, and in this case I've written h pointing in a downward direction, then P minus P naught will be equal to rho g h minus h naught, where this is g, not g of x. So we're just looking at the change in elevation. Or delta P will be equal to rho g delta h. Now it may be confusing if I put the height going in this direction this time and I had it going in this direction upwards for another instance. It's just a change in outlook. Much more important to keep track of this delta h. If we're going down in elevation, then we're going to increase the pressure. The pressure at the bottom of the swimming pool is higher than the pressure at the top of the swimming pool. So h, if we increase our distance down into the fluid, we're going to increase the pressure. And this applies between any two connected points in an incompressible fluid that's not in motion. So if I have 2 cups of water, one over here and one over there, I can't say anything about the relative pressures. If I have 2 cups of water that are connected together with a tube, then I can say something about the relative pressures. The pressures will be the same at the same heights, and if there's a difference in heights, the pressure will rise depending on how much further down in the water you go. Pressure always increases downwards. Always check your signs. Don't rely on a sign convention because the sign convention may get reversed. So just make sure that as you go down in elevation, the pressure's increasing, and you'll almost always get that sorted out really easily.